Now comes to the last talk of this session, is given by Adrian Wai, who is a software engineer at Google. After he graduation from University of Wisconsin-Madison. At Google, his current focus is on hardware transport, like this Falcon, and enable them for various use cases. So, yeah, please.
Thank you, Kai. Good morning, everyone. I'm Arjun Singhvi, and today I'm here to present Falcon, which is a reliable low latency hardware transport for NICs. Let's get started with the motivation for hardware transports. For us, there were three primary drivers. Firstly, to support new and demanding workloads, many of which are being discussed in this venue today. Specifically, high-performance computing applications and AI/ML workloads bring about a new set of requirements in terms of high operate, high burst bandwidth, and low latency. Not only that, we also wanted to satisfy the demands of existing workloads such as distributed storage, RPCs, and analytics as well. Secondly, while there have been incredible gains and optimizations done to software stacks over the years, there came a point in time where we hit a wall with these optimizations. We needed orders of magnitude improvements to satisfy demanding workloads in a much more efficient manner, precisely using much lesser CPUs. And for that, we decided to move the transport to the hardware. Lastly, the Achilles heels of current hardware transports is that they still mandate a lossless data center. RoCE, or RDMA over Converged Ethernet, as a result, is limited to niche use cases rather than general purpose data centers because of this. Let's delve a little bit deeper into why RoCE still mandates a lossless data center. Standard RoCE requires this because it relies on go-back-N loss recovery, and as a result of that, the performance is poor, as can be seen with the graph on top here, where we plot the goodput achieved as a function of inducing drops on the x-axis. And as we can see, that even under nominal drop rates, there is a performance cliff. As a result, this has mandated the use of PFCs. However, these are untenable in commercial data centers because of its operational hazards. More recently, there have been proprietary loss recovery extensions that help to improve performance under losses, as can be seen in the graph on the top right, with selective repeat, which is an extension available in CX7 NICs. However, while they provide limited improvements, it does so by violating the IBverb specification as it delivers data out of order. Not only this, selective repeat is only available for a subset of the RDMA operations. The graph at the bottom plots the loss, the goodput achieved under losses, and it reports the same performance irrespective of the loss recovery mode selected for send-receive operations. Lastly, the NIC also supports an extension called as the adaptive routing mode, which suffers the most under losses as it's presumably designed for lossless deployments. As a result of all of these limitations, RoCE is limited to niche use cases and specific deployments such as dedicated backend networks. As a result of this state of affairs, it mandated us to rethink transports in NICs. So to do so, we took a step back and asked ourselves the question as to what would we want an ideal transport to deliver. Firstly, we would like it to deliver predictable performance under diverse networks, including those that need to cater to multi-tenancy, as well as have oversubscription points. Secondly, they must be robust under stress, including losses and reordering, as it's common to happen in data centers. They should also support standard interfaces so that we can lift and shift customers seamlessly and can transition existing applications to leverage such new capabilities. Lastly, we wanted to do all of these with operational ease and allow iteration for performance fixes so that we don't require new hardware revisions for every small fix which we want to do. And with Falcon, we essentially did that. We built a data center hardware transport equipped with modern capabilities and with minimal baked-in assumptions. And we did that by bringing in a decade of advances and production experiences to hardware transports. And this was done by leveraging proven techniques to deliver low latency, isolation, and efficiency. Now I'll go over the key building blocks of Falcon which help us meet these requirements. Firstly, delay-based congestion control has been our bread and butter in ensuring that applications receive low latency and high utilization. It's something which can be implemented completely at the end host or NICs in case of hardware transports. And the key capability that it provides is that it's able to distinguish the precise point where congestion is occurring, whether it's in the fabric or the end host or the receiving NIC, to the use of precise hardware timestamps as shown in the diagram here, where T1 and T2 are essentially the TX and RX timestamps of the data being sent in the forward direction, and T3 and T4 are timestamps which the ACK takes on the reverse direction. And using these 4 timestamps, we are able to disambiguate where exactly the congestion is happening and have an appropriate response to this. Secondly, congestion-aware multiparting is something which is critical for data center applications. As all of you know, data center topologies typically have multiple parts between a given source and destination. And in Falcon, our overarching principle was to allow operations to use these multiple parts seamlessly. And we do so by allowing an operation to actually take multiple parts in a congestion-aware manner. And what I mean by this is that Falcon naturally sends more packets to a part which has more capacity or more available bandwidth and does so seamlessly. Furthermore, techniques such as protective load balancing and rerouting are something which help us to transparently migrate from a given set of parts which are, say, congested or experiencing failures transparently to other set of parts which are relatively more favorable. And we do all of this in Falcon, where we integrate them coherently with modern loss recovery schemes which are able to distinguish between losses as well as reordering. Moving on to this slide, let's give you a high-level overview of Falcon. As I said, Falcon is a hardware transport in the NIC. However, it does not directly interface with the host applications. Instead, we have several ULPs which interface to the actual host applications, and Falcon actually interfaces with the multiple USPs through a simple request-response transaction protocol. Falcon internally consists of 3 layers: the ULP mapping layer, whose responsibility is to actually map ULP ops into one or more Falcon transactions, and then the transaction and packet delivery layers, details of which we'll go into next. As you can see in this diagram, the interface to the network is via the packet delivery layer of the Falcon protocol. Having formed a mental model of Falcon, I will now go over the key design principles that enable Falcon to deliver on its requirements. The first design principle was to have native support for multiple ULPs through a layered design. The challenge here was that we wanted to support multiple ULPs without multiplicatively increasing hardware complexity. And we did this by having a clear division of responsibilities between Falcon and the ULPs, with the aim of reducing feature redundancy between the ULPs. So the core transport functionality was embedded inside the Falcon block. Moving on, the second design principle is reliable delivery with delay-based congestion control and multiparting. Within Falcon, the packet delivery layer performs these more canonical transport capabilities. And as we can see in this diagram, the upper layer protocols essentially submit transactions to Falcon, and in the TX pipeline, they sit in the per connection transmission queues and are subject to congestion control as well as part selection criteria, and are eventually sent out on the wire. The sender then receives an ACK from the receiver, processes it, and generates a completion to the upper layer protocol, which eventually gives it to the host application. Congestion control and multiparting are key enablers to ensure that predictable performance is delivered to the applications. Additionally, the packet delivery layer is responsible for ensuring end-to-end reliability between the transmitter to the receiver. And a key challenge here, which we wanted to avoid, was to avoid performance cliffs in the presence of losses. We've seen this with the results which I showed with Rocky. And traditionally, hardware transports treat losses as something which are very rare, and they deal with them off the fast part, typically involving firmware or host parts. And this leads to scalability limitations. In Falcon, what we do is that we do the retransmissions completely in hardware without any firmware involvement. We keep the necessary packet metadata, which is required to trigger retransmissions completely in hardware, and have the capability to do so in hardware. The retransmission timeouts are also handled efficiently by hardware threads scanning the packet context. Moving on, the third design principle was to introduce hardware-assisted programmability through FAE. As we just discussed, the packet delivery layer is responsible for canonical transport capabilities. However, we wanted to ensure that we can evolve the transport without requiring any new hardware revisions. And here, our insight was to do this by separating the management of transport features from the mechanism implemented in the hardware part through the introduction of FAE, or the Falcon Adaptive Engine. FAE essentially is software which runs on general purpose CPUs available in our IPUs, and it allows us to do quick iterations on certain aspects of the protocol. Looking back at the pipeline which we've been referring to, what happens here is that on the reverse part, as acts come in, apart from generating completions to the ULPs, it also generates FAE events which are consumed by FAE, and it generates a FAE response which is then used by the data part. Let's make this a bit more concrete. Communication between FAE and the packet delivery layer happens via shared memory queues using well-defined event and response formats. If we take a look at the various transport capabilities such as multi-parting, congestion control, and we distill them out, it actually consists of 3 phases. The first phase is to actually elicit signals from the network, and this is done in the hardware in Falcon. Once we get these signals, these are consumed by various algorithms which run in FAE, and they can be things with respect to modulating the congestion window or selecting the appropriate part or reparting the part as a result of congestion or failures, and it outputs transport parameters. And these transport parameters are then communicated through the response and are actually used by the data part to enforce them. So this is something which we did think quite a bit about, and we ensured that there is a rich interface between FAE and the packet delivery layer. And what we actually realized in practice was, since it was designed, it actually stood the test of time because we were actually able to leverage experiences from production, make changes to the algorithm running in FAE, and be able to get those gains without actually requiring a new hardware spin. Moving on, the fourth design principle in Falcon was to deliver ordering and performance through the introduction of on-NIC resources. As we've seen earlier, Rocky trades off between ordering and performance under stress. However, with Falcon, we did not want to trade off on either, and we wanted to provide both. And to do so, we introduced on-NIC buffers to accept packets out of order and reorder them in the hardware. Traditionally, NICs tend to avoid on-chip memories because of their area and power constraints. However, with recent process technology advancements, we've seen that having on-chip memories is feasible nowadays. And in our case, the on-chip buffers which we introduced occupied less than 1% of the die area of the entire IPU, making them feasible. And from a protocol standpoint, the transaction layer is the one which is responsible for managing these finite resources and ordering if required. So to sum it up, predictable performance in Falcon is delivered through delay-based congestion control and multiparting. Robustness is guaranteed through hardware-based reliability and the use of on-NIC resources. We support standard interfaces to the layered design. And lastly, hardware-assisted programmability through FAE allows us to do rapid iteration and makes operational easy. So we took this design that I've described, and we implemented this as an independent hardware block for integration with different vendor foundational NICs as well as IPUs. And while integrating, it actually requires integration with other features which the overall NIC provides, such as precise packet timestamping for RTT measurements, which is crucial for delay-based congestion control, or timing wheel for pacing. And finally, we got this as the Google Titanium 200 Gbps IPU, which is running in our production today. Having understood the key ideas of Falcon, let us now see how it performs. We start with how Falcon achieves real-world application scalability by scaling past the breaking points of software stacks. Falcon here is used in live migration of guest memory and addresses key bottlenecks to minimize guest visible degradation. The graph here plots the guest memory access rate on the y-axis as a function of time. Here, we compare Falcon with Pony Express, which is Google's highly optimized software stack used in production. Live migration can be thought of to be broken down into 2 broad phases. The first one is the pre-copy phase, which is denoted by the dashed lines in the graph, where the VM actually runs on the source host, and we initiate in the background bulk memory transfers to actually transfer guest memory from the source host to the target host. And as we can see here, with Falcon, the pre-copy phase finishes quicker, specifically 17% quicker than Pony Express. Apart from the pre-copy phase, then there is a brief blackout period, and then the VM is resumed to run on the target host. And during that time, the post-copy phase is initiated. And what we can see from the graph here is that Falcon significantly reduces the post-copy phase as well. And this is extremely critical for customers, as during the post-copy phase, what actually happens is that the VM is running on the target, and if it encounters a page which is not present, it does a demand fetch from this remote source host in a critical path. So having a low latency transport which gives us predictable performance is extremely critical, because if that's not the case, what actually happens is that the guest vCPU is stalling during that time until the guest page is fetched from the remote host. And what we see here is that because Falcon is able to improve the post-copy duration by improving the demand fetch latencies, it actually leads to 6x reduction in the customer visible vCPU wait time. Moving on, this graph essentially shows Falcon improvements for another class of applications. Here we show GROMACS, which is a popular molecular dynamics simulations tool used in HPC workloads. On the y-axis, we plot the simulation time finished in a given day, and on the x-axis, we plot the number of nodes. And as we can see here, Falcon's performance scales with the number of nodes. And the reason for all of these benefits is because we got the basics right with Falcon. It delivers predictable latencies under diverse conditions. As we can see from the graph on the top, where we plot the latency on the y-axis as a function of message sizes on the x-axis, we are able to deliver close to ideal latencies as the message size scales. In the bottom graph, more importantly, we plot the performance under incas. The y-axis plots the latency relative to the ideal latency expected, and the x-axis plots the incas degree. As we can see here, Falcon achieves best-in-class latency under large-scale incas, significantly better than Rocky. We now look at scalability under losses, reordering, and connection scale. The top two graphs plot the goodput achieved as a function of drop rate and reorder rate. And as we can see here, Falcon delivers stable goodput in the presence of losses as well as reordering, whereas Rocky is not able to do that because fundamentally it cannot distinguish between losses and reordering. Whereas Falcon is designed to disambiguate between these two with high precision and trigger retransmissions in a timely manner. The graph at the bottom shows the latency increase as a function of the number of active queue pairs. And as we can see here, Falcon delivers a near stable latency with increasing number of connections, whereas the alternative has a cliff towards the right side of the graph. And the reason why Falcon is able to actually maintain stable latency is because of the way it manages hardware resources with back pressure, and it handles errors properly, enabling line rate operation in a resource-constrained environment without performance cliffs. So in conclusion, Falcon marks a new era in hardware transports with significant advancements. We are no longer tied to hardware transports which have their roots in InfiniBand and lossless networks. It delivers a data center hardware transport with modern capabilities and minimal baked-in assumptions. As we've seen, it unlocks orders of magnitude gains for real-world general-purpose applications. And I also want to call out that Falcon is open source. We've released various protocol specifications which go into much more details than what we've gone in the paper. We have a high-fidelity event-driven simulator called as SIGCOMM', which we've been using extensively to develop the protocol. And lastly, we've released an at-scale RDMA benchmarking tool to benchmark RDMA at scale, something which we hope the community finds useful. Thank you.
Okay. Time for questions.
Federico De Marchi, Max Planck Institute for Informatics. Thank you for the great talk. I was wondering if there is, why you preferred in Falcon design to stick with delay-based congestion control rather than, for example, telemetry-based, like we saw in HPCC or later Bolt even.
Yeah, so that's a good question. Like one of the key things which we started with when we wanted to design Falcon was to have minimal requirements on like in-network support. That's something which we didn't want to always rely on because that's not readily available in all our data centers. But fundamentally, nothing prevents Falcon to actually adopt techniques like HPCC and Bolt as well. So yeah, that was the reasoning. Yeah.
Thank you for the talk. So do you see Falcon and similar like UET replace TCP in general purpose networking or remain limited to hardware transports only?
I think in general, there is room for it replacing TCP as well, right? But TCP has its place as well. But within the data center or across multiple data centers which are co-located, I do think that RDMA through various transports can essentially replace TCP. More specifically, Falcon has various design aspects which let it scale to larger scale as well. So I do think that we are moving towards a trend where RDMA is going to be used more and more because of its low latency and efficiency benefits.
Thank you.
Hi, great talk, Mike Silverstein, Technion. I was wondering, actually two questions. One really small, does Falcon rely on in-network synchronized clocks? It seems like it should. That's number one. Number two, did you evaluate Falcon, or do you see it used for east-west networks for data, for LM training and stuff like that? Not only for general purpose?
Yeah, so regarding your first question, Falcon doesn't require synchronized clocks because it has 4 timestamps which are taken independently at the source host and the destination host. But we do see that using synchronized clocks helps us have more appropriate congestion control response. So that's something, if the network supports, then Falcon can readily adopt it and actually leverage one-way delay. And that's something which we've been looking into. And your second question was?
It was training networks, yeah.
Yeah, so yes, the paper does go into details about how Falcon performs with AI training models as well. So it does, the results which we've shown here do hold in the context of those as well, yeah.
Okay, one last question. Yeah, over there.
Okay, thanks for a great talk. So it seems that the Ultra Ethernet transport has a quite similar network architecture comparing to Falcon. So I know Falcon is published actually earlier than the Ultra Ethernet. So can you comment on the comparison between the Ultra Ethernet transport and Falcon? Thank you.
Yeah, so the question is, how do we contrast the Ultra Ethernet transport with Falcon? Right, so Falcon, as I said, is specifically designed for general purpose data center applications. Right, the Ultra Ethernet transport, it does not really support lift and shift customers which use the IB verb specification, right? So that's something which Falcon focused on because that was a key requirement. But there are similarities as well where, for example, the loss recovery approach which both the transports use are sort of similar. So yeah, that's what I would say about the two.
Okay, thank you.
All right. For more questions, we can take it offline. Okay. And Falcon has been online. Okay. Let's thank the speaker again.